Good morning, class, and welcome to this lesson on Geometric Optics 12, Lenses in Combination. Today we'll be able to solve problems in which there are two or more lenses in combination. Well, we're actually not going to solve problems, but we're going to look at problems and how to look for tricks and how to solve them. I'm not going to actually solve any problems because you can do that in class or for your homework. So, lenses in combination. When we have a lens in combination, is one basic rule, and the rule is this. Um, the image the image produced by one lens, the first lens, is going to be is is going to be the object for the second lens. Okay, so the image produced by one lens or the first lens is going to be the object for the second lens. So when you look at a problem with lenses in combination, you need to look at it as two problems. Okay, split it in half. Okay, there's no way you can do it all at once. Just split it in half. You're going to solve everything twice, and you're going to be using all of your equations. M equals negative di over do, which is equal to hi over ho. Or you're going to be using 1 over do plus 1 over di equals 1 over f. Okay, so you have your two equations, and that's it. Just going to do it twice. Okay, so here's a picture to show you what it means. You have a lens here with an object. This object is going to produce an image here, and this image here is going to be the object distance for the second lens. Okay, so you can see here, because it breaks it down. It breaks it down here. So our object, this is the focal point for the first lens. The focal point for the first lens. This is the object distance, so that's the object distance right there. And then the image distance, this is the image distance for the first lens. And so when we come to our second problem, the image distance of the first image is going to be the object distance. So this is the focal point of the second lens. And then for this problem in particular, it's going to produce a virtual image back here. So this is the image distance too. So there's no way to simplify this. You just simply have to do the problem once. So more than likely you would solve for the image distance and the image height. So image distance and image height here, and then plug that into the next one, and then solve for the image distance and image height here. So you have to just do things twice, okay? And so be very careful with your labeling. Be very careful with your labeling. This is good bookkeeping. Good bookkeeping has to happen. Bookkeeping. Good bookkeeping has to happen here because you want to be able to label like object distance 1, object distance for object 1, image distance, just like they did here, so that way you're not confusing the two numbers. So just if you keep things clear and organized, it should work out well. If you just have a bunch of numbers on the page, you will probably mess up more than likely. Okay? So some examples of things that you're going to see that are probably going to confuse you. Let's say you are more than likely going to be given the focus for lens 1, the focus for lens 2, and the distance between lens 1 and 2. So let's say this distance here is, I don't know, we'll say 30 centimeters, okay? So you'd be given that distance. Let's say, for example, in this one, we have an object here. Well, based off our ray diagram, okay, we are going to be producing an image here, okay? That would be our ray diagram. And so you're going to have an image distance, and we'll say it's going to be, I don't know, we'll say this image distance is 17 centimeters, okay, 17 centimeters. You need to be able to calculate, more than likely, the biggest problems I see is that students will plug in 17 centimeters for the object distance for the second lens. But 17 centimeters is not the object distance. The object distance for the second lens, is going to be 13 centimeters, which comes from 30 centimeters minus 17 centimeters. So if this is the full 30 and the image is 17 centimeters away, the object distance for the next one is going to be 13 centimeters. Okay, so don't just get into the habit of plugging numbers in. Draw the picture and just label like crazy. Draw it nice and big. Do it on a second piece of paper if you have to, so that way you can clearly see what's what. So this is 13 centimeters. You're not going to plug in that number. You're going to plug in this number. Okay, so that's the first thing I want to point out. Let's say, for example, the image is within the focus. So it's within the focus, and so that means we're going to have this situation here where if it's within the focus on the first lens, we're going to have a virtual image back here. We're going to have a virtual image back here. So once again, let's say this is, you know what, we'll do a different number. Let's say this is 40 centimeters this time. And let's say the image distance here is or is 15 centimeters. Okay, so it ends up being 15 centimeters away. Now, what you're going to see here, when you solve, so let's say we do our equation. We do 1 over dO plus 1 over dI equals 1 over F. We solve this equation, and we get a image distance of negative 15 centimeters. That tells us, the negative tells us that it's a virtual image. It is a virtual image, and it's going to be located to the left of the first lens. Okay, so it's going to be virtual image located to the left. So that's how we get this. Okay, now when you do your next problem, you don't plug in negative 15. This is not negative 15 centimeters away. This sign tells you it's a virtual image located to the left. And so if we were going to do our object distance for this second lens right here, this distance is actually 55 centimeters, which is just 40 plus 15. So like I said, draw pictures, draw big pictures, label everything, and don't just start plugging in numbers, okay? The object distance is not 15, it's not negative 15, it's 55, and we found that from solving that this is negative 15 centimeters. We plug that, so we find it's negative 15 centimeters, so we have to add 15 to 55 here. So that's another example of common mistakes. So good bookkeeping, make sure you label everything. All right, our next example is one in which we have the same kind of situation. We have an object, I'll do it really close. We have an object very, very big. It's going to be enlarged here, and it's going to go this way. And I might draw this line a little bit curved here to show that. Now, that means the image produced by the first lens is going to be behind the second lens. The image produced by the first lens is going to be behind the second lens. And so, if you remember, when we did our signs, DO is negative. DO is negative if the object is right of the lens. So when we do our next equation, when we do 1 over dO plus 1 over dI equals 1 over F, for this second lens, this would be our second problem, okay? This would be our second piece. So this would be our first step, or our first problem. We would solve for this, and we'd find the image to be back here, okay? We would solve for this, and so when we plug in this number for this lens, when we plug in this number for this lens, this is going to be negative. And so just to be clear, let's say this is, I'm just going to change the number again. Let's say this is 50 centimeters. 50 centimeters. And let's say we get an image distance here. We get an image distance of 65 centimeters. We get an image distance of 65 centimeters. That makes this 15 centimeters again. So if we were plugging that into this diagram here, we would do 1 over negative 15 centimeters plus 1 over di equals 1 over f. So those are just some common things I want to point out. Okay, we're not going to plug in 65. We're going to plug in negative 15 because it's 15 centimeters to the right of the second lens. Okay, so once again, good bookkeeping. And I just want to point out A couple examples here. This is our first picture we saw. This is actually the example of a microscope. This is what a microscope does, okay? On a very basic level, we have a very, very small lens. We have a very, very small lens at the front. And this small lens has a very short focus. Okay, it has a very short focus. So we're going to take very, very small objects and we're going to make them bigger. So notice we have a larger image here. The second lens is going to be a larger lens with a longer focus. So we have a nice long focus here in which we're going to have a large image produced by the first lens, and then we're going to make sure that this image is within the focus here, so that way we have a nice big virtual image, so we can see very, very small objects very, very large. Okay, but notice because we have such a very small object, we're going to have a very small lens with a very, very small focus, so we can enlarge it. Okay, and make a big virtual image to see what we're trying to see. Okay, that's the basic level. And on the flip side of that, we have a telescope. This would be for a telescope. Okay, notice in a telescope has a very, very large lens. Okay, it has a very large lens in the front to gather a lot of light, as much light as it can. Because we're looking at stars very, very far away, we need to get as much light into that lens as possible in order to try to see our image. So the first lens has a very, very long focus. Okay, so we're trying to gather as much light as we can, very, very long focus, and the eyepiece is going to be smaller, and it's the same exact thing as a microscope. So we have a very large object making a very, very small image, and then we put it within the focus to make a final image that's larger, so we can see these distant objects, even though they're very, very small and far away. So a microscope and a telescope are just really flipped. A telescope has a large, big lens and a small eyepiece to gather as much light as it can, whereas a microscope has a very, very small first lens and a very, very big second lens. And these are almost always the examples in lenses and combination problems, because these are the two things that people use on a really a very common basis, a very daily basis that people are doing biology and or astronomy.